Okay, so midterm scores are out. Presumably all of you have seen your midterms by now. Overall, I think that as a class you did quite well. I thought there were a lot of somewhat subtle problems, but many of you did quite well on them, so that's really good. I was looking through the exams and I saw a little bit more in terms of silly mistakes than I could have hoped for. So the number one thing that points me to is that you're not getting enough sleep. Okay? Like, you need to be able to, if simple arithmetic or things where, like, you can look at the answer and you can tell that the student knows what's going on, but, like, what's on the paper isn't quite representative of the right answer. And I saw multiple solutions of this form in little places. So I think that was another thing that I noticed. And the other thing that I noticed was that sometimes an ability to stick through the calculation. Just like, you know what, this isn't quite working out, but I'm going to keep trying. It seemed like sometimes people just were like, it isn't obvious. Let's move on. And so a little bit more in terms of when you're doing the homework, when you're doing the discussions, I want you to practice this, right? I want you to, it's very easy, especially in the kind of environment that everyone is in. There's a lot of temptation to say, let me quickly look at the solution. Or maybe I got a text message that's really important. Or maybe there's something in the news that I really, really have to look at, right? And so whenever you're sitting down to do your homework, we're always constantly bombarded with all of these distractions. And especially when things get hard, when the problem isn't obvious, is when these distractions really come at us, right? So I really encourage you to, when you're sitting down and doing the homework, doing the discussions, to, set yourself a timer and say, like, hey, I'm going to sit and I'm going to think about this problem for 3 minutes. Set a 3-minute timer, okay? And for 3 minutes, you're not allowed to do anything else except think about that exact thing. After 3 minutes, you can be distracted, right? When you're sitting down to work, say, I'm not going to get up for 20 minutes, 30 minutes. Put your phone away. You say, I'm not allowed to check my email. I'm not allowed to check a text for the next 20 minutes, right? Set yourself these timers that will allow you to focus and will allow your mind to calm in a way that can allow you to focus on the problems, okay? So I hope these tips help, and I hope this helps you practice also for the exams, because there is no text message that you can check during the exam, right? And that's going to be true for a lot of things in life. Like, you're just going to need to be able to focus to get through things. So that's one of the kinds of mistakes that I saw. Not necessarily mistakes of not fully knowing the stuff, but of not pushing through sometimes when I think that maybe you could have, okay? That said, I'm sure for some of you the exam went really well and you're really happy with how you did. I'm sure for some of you the exam you feel does not represent your true understanding of the material. And both of these cases I'm sure exist. My goal and our course staff's goal is to help you improve and get better from this point forward, right? So the first thing I want you to realize is that I'm 100% certain, well, maybe shouldn't say 100%, but I'm very, very certain that you all did better on this midterm than you would have done if I had handed it out the first day of class, right? So you've learned something, which is great, and you should be happy about that, okay? Just because you didn't get to where exactly you wanted doesn't mean you should discount all of the progress that you have made, right? So make sure you celebrate your achievements. But if you're feeling like, you want to focus on, you want to change your study strategy for the final, you're not sure how you're doing in this class, you want to get advice, we have a series of one-on-ones with course staff that you can sign up for. If somehow all of these fill up, we're open to kind of bringing up more. My office hours are, of course, always available. So today's office hours I will almost certainly convert entirely into one-on-one conversations, primarily to focus on the on people who want to talk about the course content. I know there's a lot of you who also want to talk about things like grad school and future opportunities. I'm also happy to have one-on-one conversations with all of you about that. But maybe save those for a time that's not right after the midterm. So today's office hours will definitely be focused on anyone who wants to have a one-on-one conversation with me. I encourage you to come. I encourage you to come to my office hours in general. You don't have to have a question. You don't have to have a question about the course content. In general, I'm happy to just sit and chat. So please come to my office hours in general. Anything pressing that you want me to talk about regarding the midterm or anything else before I get to course content? Okay, good. So congratulations, you're done. Just one more exam in this class, and then you're out of here. The other thing that I think is very exciting is we released drafts of tentative projects for the course on the course website. The projects are a great opportunity for you to kind of get your first exposure to research, okay? A lot of students have been coming to me asking about how do I get started in research. That is exactly what we're trying to do and help you get started with this research through these projects, okay? So there's 3 different project areas. There's a project, the first one is about adversarial machine learning and neural networks for classification. And so basically the idea is about how can you think about classification that goes wrong in an adversarial way. The second project is about a long-standing open problem in control theory, which uses a lot of tools from optimization. And the third problem is, or the third project is about modifications on gradient descent, and particularly a method that is known as accelerated gradient descent, which is about getting gradient descent to converge faster, okay? They're very, very different. And the goal is to get you to read research papers, but do it in a way that is guided and not just like, here's a paper, read it, and go do your thing, right? So we will have office hours that you can use to talk about these projects. These projects are quite advanced, so not every single TA will be particularly familiar with every single project. So we will have specialized office hours and specialized staff to answer questions on the project. Right now, we've only released drafts, and I wanted to get drafts out to you just so that if you wanted to, use spring break to kind of look over things, see what they are, you can kind of get started. I don't anticipate things changing a lot, so if you get started, you're not going to have wasted a bunch of time. But these are drafts. We're still tweaking some things. The exact deliverables, the exact due dates are TBD. So these are all coming. But you will have plenty of time to complete them, but we're giving you kind of a long head start, okay? I might spend some time introducing the projects in more detail after spring break. In today's lecture, I don't quite have that much time to do them. The other thing about the projects is that if you choose to do a project, right, the projects are completely optional. You don't have to do them. But if you choose to do a project, this can be a good way to kind of boost up your midterm or your final exam grade. If you feel like you're not the kind of person who does well in a time-pressured environment, but you like, sitting and thinking on a problem for a long time on your own, the project is your chance to do that, okay? And show us how you can apply the concepts from this class on your own time, okay? So 10% of your grade from your exams will be moved to your project if you choose to do the project. And your grade will be computed in a way that is only favorable to you. So we will compute 2 grades for you, as though you did the project. Like if you do the project, there'll be the project grade in your class with the project. And then there'll be the grade as though you never did the project. Whichever is higher is the one that will be used to compute your final course grade, okay? So you cannot lose by doing the project. You can only learn something. Okay? I think that's it. All the other policy stuff is like on the website. Yes, question. They're all roughly intended to be the same difficulty. There's not like one that we've made to be easier or harder. But depending on what you like, what kind of, some are a little bit more math heavy, others are a little bit more coding heavy. So depending on what you feel more comfortable with. Some projects will be easier for some people and other projects will be easier for other people. They're intended to be different. The projects are intended to be completed in groups. You will be allowed to do at least 2 people per group, but we haven't finalized the exact parameters of how many people per group and so on and so forth. We will let you know as soon as we can. Okay? How's it going to be graded? There will be deliverables, and you will be graded on those deliverables. But it'll be pretty clear. I mean, we'll be grading the project, so we will be reading every single one and giving you a grade on them. So the projects are all outside of the scope of the class. Okay? They all draw on tools from optimization, but none of the projects will be discussed in lecture in any detail. None of the projects will be discussed in discussion. This is a research project, right? It's the cutting edge. What I'm teaching you is like 100-year-old optimization theory. Okay? Not research. So what we're trying to do is get you to the latest and greatest stuff, fast. So then let's get started with the material for today. So today I want to talk about okay? So problem transformations are a useful tool that we will end up using in this class to kind of look at different optimization problems from different perspectives. We've gone through the kind of main chunk of the module on duality, and now the rest of the course is going to be focused on more specific examples or more specific optimization problems and specific techniques to solve each of these different kinds of things, right? Duality kind of applies to every single optimization problem out there. And now we're going to go into more specialized pathways. But in these specialized pathways, these problem transformations are often useful for thinking about different problems in different ways. These are kind of almost a bag of tricks, right? So there's transformation 1, which is called the addition of slack variables. And as you saw in discussion, you did the magic with constraints problem, right? But anyways, okay, maybe it's coming in this discussion, in the discussion to come. I forgot. But basically, the point is that what you will see in that problem is that different problem formulations can sometimes lead to different solutions, okay? Or different perspectives on the solution. Maybe not necessarily different solutions, but different perspectives on the solution. And what these problem transformations do is that they will help you to think about the same thing in different ways. So let's talk about a specific problem, and then you'll see what I'm talking about. So let's consider the following problem. Okay? So this is a problem that's very similar to problems you've seen before. This is the standard least squares objective, right? And here, this is a regularizer. You've seen a different kind of regularizer before. You've seen the ridge regularizer, right? You've seen when this was kind of x, the 2 norm of x whole squared, right? That would give you ridge. Instead of the 2 norm here, I'm adding the 1 norm. This problem is what is called the lasso problem. And we're going to have an entire lecture talking about the lasso problem in a couple of weeks. That's not the lecture that I want to give today. What I want to do is I want to use this problem as an example to show you an epigraph reformulation of an optimization problem. So epigraph In particular, let me remind you that if I have some function f, right? This is f of x. This is x. What is the epigraph of f of x? It's all of this set up here, right? Remember we defined this? Remember we defined that f is a convex function if and only if the epigraph of f is a convex set? Remember that? Okay. So let's say now I wanted to minimize f of x over, let's say, x belonging to some domain x. Well, when I look at this epigraph, f is basically the set of the function f is always below the epigraph, right? If I remind myself of the definition of the epigraph of f, it's the set of all points x comma t such that f of x is less than or equal to t, right? That means that every point in the epigraph, every t that belongs to the epigraph, is always greater than the corresponding f of x, right? So I could write this minimization of f of x. Alternatively, I could write this problem as the minimization of t. Instead of minimizing over f, I'm minimizing over the t's in the epigraph such that f of x is less than or equal to t. Right? Because for every t, I look at all of these, the function value is always the smallest thing, right? So whether I choose to write my function or my optimization problem as a minimization of f of x over the x in my domain, or I choose to write it as a minimization over t such that f is always less than or equal to t, both of these are going to give me exactly the same answer. Does everyone see that? Right? Because these t's are always larger, right? I would never choose a t that's not exactly equal to f of x, right? Does everyone see that? One second. So this reformulation is what is called the epigraph reformulation. And it seems kind of trivial, right? That there's not really much use. But you'll see in this example of how it can actually be used. So how can I use this in reformulating this particular problem? Well, what is the one norm of x? I can rewrite the one norm of x as the sum of the absolute values of its elements, right? I know that this is true. Okay? And now, maybe instead of thinking about this as the sum over these absolute values have this kind of not great property, right? What is the thing about absolute values that's kind of annoying? It's not differentiable at 0, right? It's kind of like a difficult thing to deal with. Like we can't, none of our gradient descent would have a problem with this thing, right? Because it's not a differential objective function. So we can't use the same technique that we use to solve ridge to solve this problem, for example. But as we'll see, it's an incredibly important problem that has some very nice properties. So how could we rewrite it in a way that might make it more amenable for us to be able to actually solve? Well, what if I consider writing okay? And I replace every single absolute value of xi with the corresponding epigraph, right? And I say, well, xi is less than or equal to ti, right? Or absolute value of xi is less than or equal to ti. And I consider the problem Now, instead of writing this in terms of the one norm of x, I've written it in this particular way, right? Where now, when I look at this objective function, and now my optimization is over x and t here. Actually, one thing I should add up here, sorry. I should add my optimization is now also over t. Okay? Now, in x and t, is this a differentiable function? In fact, what kind of function is this? This is a quadratic program now, right? It's a quadratic objective function. Except the constraints here are still not that great, right? We had this like annoying thing in the objective function, and we just kind of moved it to the constraint. Not really that helpful, okay? But I can further rewrite this. And I can remove this absolute value. What does it mean for absolute value of x to be less than ti? Right? If it means that I'm between negative ti and positive ti. Right? So now I can rewrite this such that this is a completely linear constraint, and a constraint that I am much more comfortable dealing with. Okay? So by rewriting and reformulating this, I'm able to get this from a form that I didn't know how to deal with into a form that a standard optimization package can actually deal with. Does that make sense to everyone? So I said let's do exactly so let's say now absolute value of xi is equal to some function of x. And I replace f of x with the epigraph of f of x. Right? So I just say instead of having the absolute value of xi there, I'm going to replace it with a ti, and I'm going to add this constraint of xi less than or equal to ti. Right? That's exactly what we did up there. We replaced f of x with t, and then we added the constraint of f of x less than or equal to t. Do you see that? So it feels like a sleight of hand, right? That thing felt obvious, and then you see it here, and it doesn't feel obvious. But it's exactly the same thing. The next thing I want to teach you about is second transfer that's useful. Okay? So let's say I have some optimization problem that's like minimize f of x, I don't know, subject to x belongs to x. And instead of thinking about the minimization of f of x, I want to instead think about the minimization of some phi of f of x. Where now phi is now a continuous and strictly increasing function. What does that mean? It means that when I say strictly increasing, that means that if x1 is greater than x2, this means that phi of x1 is strictly greater than phi of x2. Okay? That means that phi maintains order, right? And so sometimes, if you're trying to optimize a function, there's something annoying about that particular function. And you want to replace it with a different function that makes things easier. The one thing that we've often done, is we've said, I want to minimize, let's say, ax minus b, 2 norm, and I've taken minimization instead. Okay? So this is f of x, where f of x is always positive, and this is f of x squared, right? Remember, x squared, f of x squared looks like this, right? In general, this is not a strictly increasing function, right? Like this decreases here, then increases here. But when you're constraining it over the positive reals, this is now a strictly increasing function. Because this is always a non-negative number, by saying I can always, without loss of generality, replace this f of x with f of x squared when f of x is non-negative, and get the same minimizer, right? The particular value of the minimization will be different, right? But the arguments for these two are always equal. Does everyone see that? Right? This you've always been convinced of. Right? We've used this so many times, least squares, right? But it turns out that that's not anything special about the squaring. You can do this for any strictly increasing and continuous function phi. Okay? One particular phi that is often quite useful is the logarithm function. Okay? And for those of you how many people have heard of the term logistic regression? Okay? Logistic regression is basically a way of trying to use the techniques of regression, which is linear regression, but in order to do classification. So what you want to do is you want to be able to predict a label, +1 or -1. You want to say, is this a cat or a dog? But you want to do it in the style of regression, right? In the style of least squares. Okay? I don't have time to go through the full example on logistic regression today. I'm fairly certain we have it written up in the course reader, or if you're really interested, I'm happy to talk to you in office hours, or maybe go over it in another lecture. But logistic regression uses the logarithm function, phi. For those of you who have taken a probability or a stats class, you've come across probably the likelihood functions, right? Maximum likelihood estimation. Anyone's heard of this? Right? You had a homework problem on this actually as well, right? The connection of maximum likelihood and ridge and MAP. Again, here, often people consider the optimization of the logarithm of the likelihood function instead of the likelihood function itself, because it's easier to deal with, right? So these are ways in which this particular technique is very useful. We're not going to go through it in much more detail today because I have a lot of other content that I want to cover. Normally, do we want it to be differentiable? It would be nice if it was differentiable, but this property will hold only with continuity, right? There might be reasons you want to choose it as differentiable, but not for this property to hold. It must be strictly increasing on the domain that you're considering. Correct. Okay, good. So with that now, I can come to introduce you to linear programs, okay? You've already all been introduced to linear programs. We've seen them. You already computed the dual of a linear program. But linear programs are programs basically where your constraints and your objective, everything is all linear. And the thing we love about linear programs is that they're easy to solve. And they're very, very useful for representing lots of different things. For example, whether or not you should get into a winemaking business, right? So in general, some function of the form C transpose X, AX less than or equal to B, is your general kind of formulation for a linear program. you might sometimes write a linear program with equality constraints. You might sometimes write it with inequality constraints. There's different ways of rewriting these. If you had an equality constraint, if you had something like, for example, one can always convert this into the standard form of AI transpose X by rewriting this as less than or equal to BI, and this is a way of representing an equality constraint as an inequality constraint. If you had a greater than or equal to, you could multiply both sides by -1 to always convert it into a less than or equal to. So there's nothing lost by writing this as less than or equal to, or writing this without an equality constraint explicitly, right? But in general, a linear program could have equality constraints and inequality constraints. Okay? There is something which is called the standard form of an LP. And to be honest, different textbooks use the terminology standard form slightly differently. So some textbooks might call this inequality perspective a standard form. Many textbooks will use the following terminology that I'm going to talk about: min, So one way of writing a standard form of a linear program is to write a minimization of C transpose X subject to now only equality constraints. AX is equal to B, and X is always greater than or equal to 0. Okay? So this is a very specific way, right? And it might seem that this is a very restrictive way of writing a linear program, right? It doesn't seem as general as this. Turns out that this is exactly as general as this. And any program of this type can be rewritten to be exactly of this type. Okay? So So how does one do this? Okay? So the first problem clearly is, what do you do with inequality constraints, right? How do you make inequality constraints into equality constraints? That seems like a problem, right? So the first trick is use slack variables to convert I should mention, by the way, that here, this trick, which I called the epigraph reformulation, is also often referred to as the use of slack variables. And slack variables, basically, I mean this new TI that I've introduced, right? This new TI that I introduced, which increased the dimensionality of the problem, but kind of allowed me to do some kind of reformulation. That is basically a slack variable that I'm including into my setup. Okay. So let's say I had some constraint of the form Okay? Let's say this was my constraint. How could I rewrite this as an equality constraint now? With maybe adding some variables in. Maybe take a minute to see if you can figure this out on your own. Worth that 1 minute of thinking. So how do we deal with this? Anyone? Yeah. Someone not in the front row maybe who doesn't always speak up. Yeah.
You can use the Lagrangian idea from previous.
Ooh. You could use the Lagrangian idea. Okay, so you want to try and move it into the objective function. That's a very interesting idea. You could do something like that. The challenge with doing something like that is that then you're like reformulating the problem entirely, and now your objective function is also different. Because it's a linear program, in many cases strong duality will hold, so you won't necessarily lose anything. But it's a great idea. It's not the angle we're going to take right now, but I commend the idea. Yeah, that's basically what we're gonna do is we're gonna say, look, if this is your constraint, I have AI transpose X is less than or equal to BI, right? So there's a gap between these. If I know that there's a gap between these, the idea is to let's look at the distance between them, right? So I know this is smaller. That means that AI transpose X plus something is equal to BI, right? This is what I'm going to call my slack variable. But I want to make sure that this encodes the spirit of this constraint, right? So if I just rewrite this as this, are these two things equivalent? These are not, right? But is there a way to force them to be equivalent? What constraints would you add to this? Yeah, or someone else maybe, yeah? If I added the constraint that SI is greater than or equal to 0, that then enforces that this thing must be smaller than this thing, right? Does everyone see that? So now I've added dimensionality, I've added variables to my problem, but I've maintained SI greater than or equal to 0. So my only inequality constraints are of this form, SI greater than or equal to 0. And I've transformed my inequality constraint into an equality constraint. Right? It's kind of cool. It comes at a cost, though, right? Because now you've increased whatever computation it would have taken. Now there's one more dimension that you have to search over, right? So you are paying a cost for this. It's not free. Okay? Good. What's the second issue that can arise? Well, we've converted all our equality constraints into inequality constraints, but we might still have variables that are negative, right? Here we have this non-negativity constraint. So how do we ensure that everything is non-negative? Or just maybe, not even, I want to say negative, maybe unconstrained. Right? So I might have whatever, I do everything, but I might end up with some xi that doesn't have a greater than or equal to 0 or less than or equal to 0 constraint, right? So how do I deal with this kind of situation? Do you want a minute to think about it, or do you want to? Okay, think about it. Take a minute.
Sorry, could you give me an example of such a situation?
Okay, so let's think about a specific example. In particular, let's consider the setup. Let me copy the one that I have. So here what I have, I clearly have a linear program, right? I have one inequality constraint, but we already have a mechanism for converting this inequality constraint into an equality constraint. I have one equality constraint. This doesn't bother me. This is in the form I want. And x1 is a constrained random variable in the sense that it's restricted to be greater than or equal to 0. x2 is unconstrained, right? But this is now not in this form because I don't have all of my xi's greater than or equal to 0. Does everyone see that? So how could I rewrite this in a form that looked like that? That's the question. OK, now take a minute to think about it. If it helps to think in the context of the specific example, go for it.
14.
This is equal to 14, yes. I mean, these are just, whatever, it doesn't matter. I just made up some numbers. OK, so how do we go about doing this, right? So the key thing to observe here is that any real number can be written as a difference of two non-negative numbers, right? So if I have 3, for example, I can write 3 as 8 minus 5, right? If I had minus 3, I could write it as 5 minus 8, right? But I can always write any real number as the difference of two different non-negative numbers, right? So what I'm going to do is I'm going to say let x2 be equal to x2 plus minus x2 minus, right? Where now x2 plus is greater than or equal to 0, and x2 minus is also greater than or equal to 0, right? So again, I'm adding a variable, but I have now gotten constraints on the variables that I have, right? And so if I wanted to rewrite this whole thing, I'm going to replace x2 this way. What am I going to do for this thing? I know how to deal with that. I'm going to rewrite this as x1 plus x2 plus x3 is equal to 3, and x3 greater than or equal to 0, right? So my entire rewrite of this program is going to be something like min 2x1 plus 4x2, x1 plus x2, or x1 plus now x2 plus minus x2 minus plus x3 is equal to 3.
Wait, where did x3 come from?
x3 came from this. Then I have 3x1 plus 2x2 plus minus 2x2 minus is equal to 14. And then I have x1, x2 plus, x2 minus, and x3 are all greater than or equal to 0. Yes? Where are x2 plus and x2 minus defined? I'm defining them as, I'm just writing x2 is equal to this. That's how I'm defining them. I'm optimizing over them, right? These are optimization variables now. I'm saying, so I said 3 is equal to 8 minus 5, but it's also equal to 9 minus 6, and 10 minus 7, and 11 minus 4, right? So I have so many different choices for expressing a particular number as the difference of two non-negative numbers. OK? So I'm allowing myself to choose over them. Sorry, it should be less than or equal to 0. So then I would say minus x3 greater than or equal to 0. Correct. Thank you very much. So why don't we have to include this x2 equals constraint? Great question, right? Here, I could write x2 equal to x2 plus minus x2 minus. But the better way to do it, which I should have done, is I should write this as 4x2 plus minus 4x2 minus. So I basically eliminate x2 entirely by not even bringing it up, right? So this is what I should do. So again, just to recap, I replace x2 with x2 plus minus x2 minus, and I replace it in the objective function as well as in the constraints. And now I have x1 plus x2 greater than or equal to 3. So now I have x1 plus x2 plus x3 equal to 3, but I have negative x3 greater than or equal to 0. And these are the constraints I end up with. Yes, question? So I haven't bounded x2. x2 can still be negative, right? But x2 plus and x2 minus cannot be negative. OK? So everyone see how we can take any kind of linear program and put it into the form that we've called the standard form. Make sense to everyone? OK. The standard form is one of the common ways in which is used to run the simplex algorithm, which is the standard algorithm which is used for solving linear programs. And I'm hoping we're going to get to the intuition of why the simplex algorithm works in the remainder of this lecture. Let's see how far I get. OK? Good. Next. So one of the important things about LPs is also to think about how we could so I have, let's say, some LP. Now I'm going to write this as minimize minus x1 minus x2, subject to, let's say, x1 plus 2x2 less than or equal to 3, and 2x1 plus x2 less than or equal to 3. OK? Let's consider this optimization problem. Let's call this the x1 axis. And this is the x2 axis. OK? So what is the feasible region for this problem? Can you sketch the feasible region? Take a minute and do it while I'm doing it. Don't just copy what I'm doing. So what are my two constraints here? This is 0. x1 plus 2x2 less than or equal to 3. So what are my two intercepts? When this is 0, this better be 1.5. When this is 0, this better be 3, right? Similarly, this is 0, this is 3. This is 0, this is 1.5. Right, so I can draw my two lines here. And I'm now looking at the feasible region. So that's everything below this line, right? I want less than or equal to 3. So what is my feasible region here? So I want everything that's below the first pink line and below the second pink line. So that gives me this intersection, right? So it's everything here. Right? This is my feasible region for this problem. OK? So now how am I going to try to find my optimum point? What is my objective function here? It's f naught of x. And can I write this as This is my, if I can write this in the standard form, right? This is C transpose X. What is my C transpose here? Or my C in this case? -1, -1, right? So which way does C point? What is the gradient of my objective function? The gradient of my objective function, right? This is C, right? Points that way. Okay? So the gradient is pointing me in which direction? But what is it corresponding to the, whether the function is increasing, decreasing? If I move along the gradient, I increase, right? So if I want to find a minimum, what do I want to do? Which direction do I want to move in? What do we do in gradient descent? The opposite direction, right? So I want to move in the direction of negative C, right? The direction I want to move in is this, which is negative C. Right? Everyone see that? So now, if you were to draw level sets of this function, what are the level sets of this function going to look like? The level sets of this function are everything where -x1 -x2 is a constant, right? So what are the lines where -x1 -x2 is a constant? x2 equals -x1, right? So they're like this. So this is the level set equal to what level? What's this? 0. Then I have, right? This is what my level sets look like. So now with this, intuitively, where are you going to find the minimum of this function? You're going to keep pushing in the direction of negative C. How far can you go? You're going to go to this point, right? This is a particularly nice symmetric setup, but you're seeing that basically the optimum is going to be achieved here at this particular vertex, right? This intersection of the constraints. Does everyone see that? In general, to solve a linear program, you're going to always be moving in the direction of the negative gradient, right? And because it's a linear program, your negative gradient is really easy to find, right? It's always minus C, right? If C transpose X is your objective, you're always moving in the direction negative C, okay? And you're going to keep going until you can go no more, okay? And so do you see intuitively here why we say that for a linear program, you're going to have a solution that's going to be at a boundary? Right? Anytime I have theorem, which we're not going to prove, but if I have any function that's min C transpose X, X belongs to some function, some domain X, then your optimum will be at a boundary point. Okay? I'm not saying a vertex. What are the boundary points of this? The boundary points are anything along this boundary of my feasible region, right? Except now, for example, is it possible, here I just happen to have this setup. Is it possible that, for example, if instead of minimizing minus x1 minus x2, if this was minimize x1 plus x2, which way would my gradient be pointing? That way. Which way would my negative gradient be? This way, right? And then I'm keep coming down, 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 down. I keep descending. What is my minimum? Negative infinity, right? I'm not hitting a boundary, right? So this is only true if X is bounded and closed. right? If I have an open set, I might not have my optimum at a boundary, right? Does that make sense to everyone? But this is the intuition. So further, in the case of linear programs, we can go one step further, right? We can go one step further and say not just that your optimum will be at a boundary, but you can say, in fact, it will be exactly at a vertex, okay? And what we're going to do, let's see if I have, is prove this exactly for you, okay? So, let me define a polyhedron. A polyhedron, basically the set of all points when you have a bunch of linear constraints and you put them together, okay? So any set of this form is what is called a polyhedron, okay? If a polyhedron is bounded, it's called a polygon, okay? This is just terminology. You all kind of already know what a polygon is anyway, right? But basically, the constraints of a linear program are always going to form a polyhedron, right? Because basically, you have linear constraints. This is saying take all those constraints. That's what's called a polyhedron, okay? Now what I want to define for you is an extreme point or a vertex of a polyhedron. Okay? So an extreme point, intuitively, let's say I have some polyhedron like this, right? You know that you want these things to be the vertices, right? Like, that's what we intuitively think of when we think vertex. We want these intersections of constraints to be vertices. How do we define this in a way that, like, you can algebraically manipulate these things, right? So what's the thing about this vertex? Well, like, if I'm approaching a vertex, I can keep coming at it from this direction, but as soon as I hit the vertex, I can no longer kind of continue in that direction, right? Like, I kind of have to switch directions to stay in the polygon, right? So a point x belonging to a polyhedron P is an extreme point of P if we cannot find two vectors y and z belonging to P that are distinct from x such that so if you cannot express x as a convex combination of two other points, okay, in the polyhedron, but x is still a member of the polyhedron, then it must be an extreme point, okay? So for example, if I take some point on the boundary here, this x, can I express this x as a convex combination of 2 points? I can take, something here and something here. Like, this is half y plus half z for this, right? It's on the line segment that connects. Remember, what is the convex combination of 2 points? Like, the line segment connecting 2 points is the set of all the points that are the convex combinations of those points, right? So if the line segment connecting y and z is the set of all the points that are convex combinations of those points. So if I cannot find x on a line segment, right, of 2 points that are in the polyhedron itself, it must be an extreme point. Right here, for example, I cannot find this on a line segment. Because I can go this way, but I can never find the other guy. Right? But on this boundary, I can find that. In the interior, I can find that. But only for these vertices can I not find that, right? That is what is the definition of an extreme point. Polygons are not always convex sets, no. You could have a polygon like this.
So would that the middle point of the D be a vertex set? No, right? Because you could find 2 things on either side.
Good point. You're right. Polygons are always convex sets. Sorry, my bad. You're right. This is not a polygon. My mistake. Good point. Everyone caught that? Polygons are always convex sets. You're absolutely right. Because this is always a convex set. Okay. I want to remind you of one more definition that's useful. Convex hull, okay? We defined this a long time ago, but you might have forgotten. So the convex hull of a bunch of points is basically the set of convex combinations of all of those points, right? It's the smallest convex set that contains all of the points, okay? In particular, for example, if I have points P1, P2, Pk, the convex hull of these is given by the set of all x such that x is equal to sigma alpha I pi. I is going from 1 to k. Alpha I greater than or equal to 0, and sigma alpha I equal to 1. Right? Take the convex combinations of all of the points, and that's what gives you your convex hull. Okay? 2 properties of polygons. One, the polygon can always be written as the convex hull of its vertices, which answers your question again in a different way. Okay? And 2, polygons have so these are both statements that can be proven. The proof in particular of the second thing is a bit involved, and so we're not going to do it here. But I'm just going to get you to accept it on faith that if you have a polyhedron that's bounded, it's going to have a finite number of vertices. Okay? Too much topology and geometry to actually be able to prove that here. But you'll give me that for this lecture, hopefully, without proving it to you? Okay. Thank you. What? What are circles?
I was told once that circles have an infinite number of
Circles are not polyhedrons or polygons.
circles are not polygons.
Nope. Polyhedrons are the intersection of linear hyperplanes, linear half spaces. Okay. So now I want to prove for you a theorem which says let P star min C transpose X over X. And let's say we have it in standard form. Okay? Let's further assume that omega, which is equal to basically the set of X, such that okay, so I'm assuming that the domain is bounded. If the domain is bounded, then the optimal value is achieved at a vertex. Okay? So what this is saying is that there will be some vertex which will have the minimum value. Does that mean that there are no other points where the minimum value is attained? No, there might be others too. But at least one of the vertices must also attain the minimum value. That's what this is saying. Everyone clear on the statement? Okay? And the way we're going to prove this is kind of the standard bounding way in which we've proved things before, right? So we're going to say, look, the optimum value must be greater than or equal to the value at the vertices. And clearly we can achieve this value at the vertex. Therefore, it must be the optimal. Okay? Kind of, we've done this argument before, right? We find something that's the optimal value, and then we have a bound for it. Right? Okay. So for the proof, let's just say V1, V2, Vk are the vertices of the polygon, right? If these are the vertices of the polygon, this means that any x belonging to omega, which is my polygon here, can be written as a convex combination of the vertices, right? Because I know that the polygon is the convex hull of all of its vertices. Okay? So therefore, x belonging to omega, I can write as x is equal to sum alpha I vi, where the alpha i's must be greater than or equal to 0, and the sum of the alpha i's is equal to 1. Okay? So now I want to think about my optimization problem, right? I want to think about this min C transpose X, okay? So if I look at this C transpose X, I can write this C transpose X as C transpose So I can rewrite this also now as sigma alpha I C transpose Vi. And you've seen something like this before, right? Where you have kind of these i's summing to 1, then you have something that also depends on I. And you say, let's replace this with something else so I can pull out this sigma alpha I equal to 1. Right? So this is always now greater than or equal to the min over j C transpose Vj. So look at all of these terms, pull out the smallest one, and I can always use this as a bound, right? But now this is a constant, which I can just say is equal to now the min over j C transpose Vj times sigma alpha I. But this thing is exactly equal to 1, right? So C transpose x, my objective function, is always greater than or equal to the minimum of the objective function across all of the vertices, right? Therefore, the minimum must be attained at one of the vertices, right? Clearly, one of the vertices attains this minimum, whichever that minimizer is. This is the foundation for the simplex algorithm, right? What does the simplex algorithm say? The simplex algorithm says when you have a linear program, look at all the vertices, right? Look at, say, sit at one vertex, look at the value. Now look at your neighboring vertices. Is there any one where your objective function is lower? If it is, okay, go to that vertex. Now look at your neighbors there. Is there any one where the objective function is lower? Okay, go there. If you go there, great. If you cannot find a neighbor that is lower, stop. So this is not a proof that you will always get to the minimum vertex, but it is what is called a greedy algorithm, right? Keep searching the vertices until you find the best. Turns out that this works in practice. There's a lot of other intricacies to the simplex algorithm that kind of you are needed to make it work for unbounded cases and to make this efficient and to make it computable. But this is the key idea. If you want to learn more about simplex, go take 170. With that, we're done. Have a great spring break. Relax and take a breather. See you next class.